Well, good morning. I fixed that assignment on, or the due date on the assignment. I was thinking yesterday was the 3rd of May still. Oh well, let's see. Oh, I was going to look up the pronunciation of something we're doing today on Wikipedia just to be sure. The pronunciations guides on Wikipedia are not easy to use. Okay. Looks like it's Savart, maybe. Nope. Savart. That's what we're doing today, is the Savart law. So let's dive into that. And blow up this thing. Guess that light's on. And looks reasonably good. Okay. All right. So far in magnetism, all we've been studying is the effects of magnetism and not what produces a magnetic field. And so today we finally start doing that. And we'll start with just the magnetic field of a single moving charge. And let's see, for a point charge or just a little moving charge, the magnetic field produced by it ends up being this. And I'll tell you what that constant is here in a minute. Okay, so things that are in here, it's got a proportionality constant, which is fine. It has the value of the charge in there, which you would kind of expect. A moving neutron won't create a magnetic field due to its motion. It's got a cross product, which they seem to be showing up everywhere we do anything in magnetism. In this case, it's V cross R hat, where R hat is a unit vector that points from the point charge that's moving to whatever place we're calculating the field at. And it's inversely proportional to the distance squared. So we could say it gets weaker with the square of the distance various ways. Now about that mu naught. This may seem crazy to you, but mu naught's value is 4 pi times 10 to the minus 7th Tesla meters per amp. And let's see if that'll give us what we need here. This will have meters per second over meters squared. It'll end up being 1 over meter seconds. Oh, we've got coulombs too. Let's see, coulombs over meter second. Yeah, that kind of makes sense. That'll do it. But the 4 pi in here may puzzle you. Why bother writing it like this? Actually, it's one of those kind of mysterious things that shows up. And the speed of light, if you develop the wave equation for light from the equations of electricity and magnetism, not all of which we'll get to, but built into the wave equation for light is the speed of it. And the speed, pulling constants out of that wave equation, ends up being this: mu naught epsilon naught. That's supposed to be a mu naught there. So that's kind of a mysterious thing. Now we know that epsilon naught is at 8.85 times 10 to the minus 12, bunch of units in there for it. So it's kind of a weird value. C is an exact number, but it's interesting that the relationship between mu naught and epsilon naught somehow has pi worked into the mix, and it shows up when you actually solve for epsilon naught. So just kind of a mysterious thing that happens. It's sort of like, I don't know if you've done enough math where you've run into e to the I pi. I is the square root of -1. This thing ends up equaling -1. So go figure. But don't worry about it. Anyway, this is the magnetic field of a single moving charge. And so we'll start off with just a couple of examples looking at that today and see where those things go. And I sort of blew these up, and I'm still working on tests. So I ran into a bunch of problems with the Physics 114 test. I had 2 students submitted PDFs that I couldn't open. One student took the wrong test. He took the practice test instead of the real test. And okay, those things bring me to a screeching halt when I'm trying to get them done. So calculate the magnetic field at a distance of 5.3 times 10 to the minus 11th meters for an electron moving at that speed, 2.2 times 10 to the 6 meters per second. Don't know if you remember it or not, but yesterday we calculated the current that would be produced by an orbiting electron, and it was orbiting at this distance from the proton and moving at that speed. And from that current, we calculated a magnetic moment for that electron. Well, now we're going to be calculating the magnetic field that an electron would produce that distance away from it when it's moving at this speed. And it so happens that that would be the magnetic field experienced by the proton. And the electron, in the Bohr model at least, would be always this far away and always moving at that speed. So let's see what we have here. Draw a picture first. We could imagine here that here's our field point. I'll just put a letter P over here. And our little electron is moving along in this direction, and we'll imagine what's the field it produces at this instant. Now, magnetic fields travel through space at the speed of light, so there's going to be a delay between when the electron is here and when its field that it produces when it's here gets to this point. It's only going this far, 5.3 times 10 to the minus 11th meters. So traveling at the speed of light from here over to here isn't going to take long, but it's not instantaneous. So that's the direction of the velocity of the electron there. So here's our 5.3 times 10 to the minus 11th meters right there. And let's take that expression we've got, that B is mu naught over 4 pi q v cross r hat over r squared. Okay, well, let's work out the v cross r hat part. V is in this direction. R hat points from the charge to where the field point happens to be. So that's R hat. V cross R hat would point up, but the charge on an electron is negative. So the charge of this electron is going to point down. And if you consider the electron moving in a circle, that V would always be tangent to the circle, R hat would always point in toward the center, and you'd always have the same magnetic field that's being produced by the electron, because if it's going around at constant speed. Now, electrons do not act like point particles, at least as where they are in space. They spread themselves out, but they produce magnetic fields as if they were point particles. So this is just some of the weirdness of quantum mechanics. It's sometimes referred to as the wave-particle duality. But let's go ahead and calculate what's going on here. So we know the direction of the magnetic field. It's going to be in that direction. And if I make a coordinate system here, x, y that way, and z would be coming out of the page at us. So it's coming that way. X or I hat cross J hat is equal to K hat. So that's why we have that. But that means the magnetic field of this electron is going to be into the page. So it'll be in the minus K hat direction. So in this case, we'll have mu naught over 4 pi Q V R, whoops, R hat, which is the magnitude of R hat. That's just 1 over R squared. And the direction is in the minus K hat direction. So now we can just plug in the numbers to see what we get here. 4 pi times 10 to the minus 7th divided by 4 pi is equal to 1 times 10 to the minus 7th. And there's an infinite number of significant figures on that, just like there is on pi. And I can never remember the units of this one. Tesla meters per amp. Must be some nicer way to express that, but I can't think of it. Okay, and then the charge on the electron, 1.60 times 10 to the minus 19th coulombs. V, always running out of room. I should start farther left on the page. It's 2.2 times 10 to the 6th meters per second. That's that part. And still, this is in the minus K hat direction. And then R is the 5.3 times 10 to the 11th minus 11th meters squared. Okay, well, if I just think about the coulombs times meters per second, that could be a coulomb per second times a meter. Coulomb per second is an ampere. That'll divide with that ampere. Then I've still got the meter here, but I've got meters squared on the bottom, which gives me meters on the bottom just to the first power, and that'll divide with that. So I'll end up with Tesla for the strength of my magnetic field. So B is going to be, I'll put a minus sign on it right from the start because that's its direction. There's a lot of numbers to plug in for these things. That big? 10 to the minus 26, 10 to the minus 20th. Yeah, I guess it is. 3 sig figs, 2 sig figs. So it looks like minus 13 Tesla in the k-hat direction. That's a strong magnetic field. That's as strong as the ones in an MRI machine. So the electron definitely experiences a strong magnetic field. And that's just from one little electron, although it is crazy close to the moving electron. 5.3 times 10 to the minus 11th meters is not much. And when you've got something that gets weaker with the square of the distance, it also gets stronger with the square of the distance, sort of, when you make the distances very small. So there's that. Let's see. We haven't done, I thought I had another point charge moving in here, but I don't see it right now. I guess not. Okay, well, we're diving into a wire right off the bat then, and seeing how that will work out. So we want to calculate the magnetic field P at a distance x from a straight wire carrying a current I. Okay, so don't have that on here, but the current's going in that direction. And the necessary dimensions are shown in the drawing. Looks like right here is the origin. And so this would be where y is equal to 0. So we go from minus y1 up to y2. And this is extending this idea of the, let's see, I don't want to say that. Extending the idea of just a point charge's magnetic field, and the magnetic field of the point charge is just this thing B equals mu naught over 4 pi times Q V cross R hat over R squared. When we have a wire, what we'll do instead is think about just some little increment of the wire that's going to have some volume, and it'll be carrying a whole bunch of moving charges. And in that case, the magnetic field of a little element of the wire is going to be, again, it'll have mu naught over 4 pi in it, but it will look like this. I dl cross r hat over r squared. And dl would be a little length of the wire that's, as a vector, it's pointing in the direction of the current flow. So with the I in there equaling NQ, what is it? N is the number of charges per unit volume, Q is the charge on each one of those. V sub D is the drift velocity, and A multiplies that. Yeah, and I think all of that together gives you a whole bunch of little moving charges. So it's all taken care of in here. We're not going to deal with situations where we'll have varying amount of currents in various places. We'll do a couple of circular or curved current loops when we're using this law, but that's the basic idea. And this is, by the way, is the Biot Savart law, They're both French, and so you don't say the T's on there. And in French, they probably pronounce it some way fancier than what I just said, but that'll be good enough for us today. It is not Biot Savart, so just remember that. So again, let's figure out the magnetic field at point P due to some little charge there. And our distance R here is going to equal x squared plus y squared. If this is the origin for y, it's where y is equal to 0, then this would be some y value down there that's going to be a variable. And so in this case, it'll be x squared plus y squared. And that's just the Pythagorean theorem to figure out that little distance chunk there. And it's r squared that shows up in our thing. So we'll get that. So what about the magnetic field due to this little chunk of current? Well, it's going to be dB equals mu naught over 4 pi, our constant that will be so important, I dl cross r hat over r squared. Okay. Now think about the geometry here. dl is going to point in the direction of the current flow, so we could think of it as dl is going to equal dy in the j hat direction. R hat will be a unit vector that points from here to here. dl cross r hat is going to go into the page. Well, with x and y going that way, z is out of here. dl cross r hat will equal, let's see, I'm not going to try to express r hat in terms of anything. I'm just going to think it's a unit vector that points that way, and dl cross r hat will point in the negative z direction, and the angle that shows up here is going to be this angle theta. So I will have the magnitude of dl, which is just dy, magnitude of r hat, which is just 1, the sine of the angle between the two vectors and the cross product, so that's going to be the sine of theta. And I'll express that in terms of probably x and r here shortly. We'll have that. And it's going to be in the minus k hat direction. And it turns out it doesn't matter where you go on this wire, a little chunk dl down here or dl up here, no matter where you go, this is going to point in the same direction, because dl will lie in this plane, r hat will also always lie in this plane, and when you take the cross product of two vectors that lie in a plane, the direction of the cross product will always be perpendicular to that plane. So that's a characteristic of the cross product. All right, so we've got that so far. Other things we might need. Oh, we can now, I think, express dB here. Okay, or a little bit differently. It'll be mu naught over 4 pi I, the dl cross r hat ends up being this, dy sine theta in the minus k hat direction. And then on the bottom here, we've got r squared. So let's do a little bit of work and see what we can do with this. We know what r is. It's equal to the square root of x squared plus y squared. The sine of theta is going to be x divided by the square root of x squared plus y squared. So Now, will it also equal that? Trying to think, when we get up to here, and I've got my dy going in that direction, dy cross r hat is still into the page. I guess it'll be the sine of theta. It'll just be for a bigger angle than 90 degrees, but it's not a great disaster anyway. Okay, well, got the sine theta there. This is actually the square root of r, or, yeah, you could think of it that way, or r squared is just plain x squared plus y squared. What this will end up being is mu naught over 4 pi I dy x divided by, it'll end up being down here, x squared plus y squared to the first power because it's r squared, and then also to another half power, so it'll be x squared plus y squared to the 3/2, and that's in the minus k hat direction. So, whoops, that's our dB that's equal to that, not this thing. So draw a little boundary there. Well, B is going to be an integral from here to here, the magnetic field due to that thing. And so that'll be, I'll pull out all the constants, which are mu naught I x over 4 pi, and then the integral of dy on top, and x squared plus y squared to the 3/2 on the bottom. And we have a minus k hat, which I could stick maybe out front here. And my limits of integration will be from minus y1 up to y2. And this should be one of the integrals on that sheet that I gave you a while back. Oh, there's the physics 114 formulas. Where'd I put yours? I don't know. Oh, well, I know where I got them. They're in the back of the book here, just out of your appendix. Here they are, integrals. So what's this integral look like? It's actually dy over x squared plus y squared to the 3/2, or let's see, we got, here we go, dx over x squared plus a squared to the 3/2. It's the same integral. It just happens to be in terms of x instead of y. We will replace a with x and x with y. And let's see. So let me write this over here on a piece of scratch paper. And I'm going to write it down as if it was translated. The integral of dy divided by y squared plus x squared to the 3/2 ends up equaling 1 over the constant term squared, that's the x squared, times y divided by the square root of y squared plus x squared. Okay, that should be usable. Let's see, so there's our integral to do. mu naught I x over 4 pi in the minus k hat direction. Now the integral is going to be 1 over x squared, let's see, y over the square root of y squared plus x squared. And remember that y is the variable of integration, and I'm evaluating it at minus y1 and y2. Okay, let's see. I'm going to pull as much junk out front as I can. Mu naught I over 4 pi and minus k hat. And I did not lose my x. I've got x over x squared here, so I'm going to have a 1 over x. And then when I evaluate this integrand here, the 1 over x squared multiplies it, evaluating it both places. But I'll have y2 on top over the square root of y squared, whoops, y2 squared plus x squared. And then minus, well, I'd have minus y1 on top. That actually makes it into plus y1 divided by the square root of y1 squared plus x squared. Okay, well, going back to the picture here, y2 is this little distance here. The square root of y2 squared plus x squared is this distance here. So y2 divided by this distance is actually the sine of this angle up here. And I could call this theta 2 if I wanted to. The other one is y1 divided by the square root of y1 squared plus x squared. That ends up being the sine of this angle here, all the way from the horizontal down to here, which is theta 1. And so instead of a bunch of things to evaluate, I'm going to write this expression as the magnetic field equaling mu naught I over 4 pi. I mean, you could just leave it this way. That pretty much finishes the problem, but I want to do it this way. 1 over x then, and then we'll have the sine of theta 2 plus the sine of theta 1. Okay, now I could evaluate this thing for an infinitely long wire, because if you think about it, if you make this wire infinitely long, what's going to happen to theta 1 and what will happen to theta 2? Those will both go to 90 degrees. Okay, if that's the case, sine of 90 degrees is 1. I'd end up with 2 inside of here, and my magnetic field, I'll just say infinitely long wire, magnetic field is going to equal mu naught I over 4 pi times minus k times 1 over x times 2. Well, the 2 up here with that down there just gives me a 2 on the bottom, and I'd get B is equal to mu naught I over, gonna bring the x under there, 2 pi x, and in the minus k hat direction. Okay, So the magnetic field out here, due to this wire, is going to point into the page for an infinitely long wire. And we just picked one possible point. Anytime you're at a distance away from the wire, that point that you're using for your field point and the wire will determine a plane, and the magnetic field is going to be into the plane. We can draw a picture for that. Suppose this is our current carrying wire going like that, and it's a very long wire. Okay. The magnetic field of that long wire ends up being, this is a wire current going into the page there, ends up being concentric circles around the wire, and the strength of that magnetic field ends up being, if we say this is the distance r, the strength of the magnetic field will be mu naught I over 2 pi r. So, whoops, it's the magnitude of the magnetic field. And its direction you can get from a weird sort of right-hand rule. If you point your thumb in the direction of the current flow, the fingers of your right, and it has to be the thumb of your right hand, the fingers of your right hand can curl in the direction of the magnetic field. So just from that one example, we figured out a whole bunch of things. First, we figured out the magnetic field strength for that particular situation, but then we took it and made the wire longer and ended up with that expression. And by changing the viewpoint a bit, we can look like this. And so you'll have a magnetic field that gets weaker with 1 over the distance. Now, the reason it gets weaker with 1 over the distance and not 1 over the distance squared is because the wire is infinitely long. It was like the electric field of an infinitely long wire dropped off like 1 over r as well. So that's something that happens. All kinds of stuff just in our first Biot-Savart law example. But we'll be able to use this idea in quite a few of these problems. So let's go on from there. Hey, look at this. A long straight wire running in a north-south direction is 0.65 meters above a compass. How much current must flow in the wire and in what direction to make the compass needle point 30 degrees east of north? Huh. Well, that's kind of interesting. So we'll just imagine this wire here that's running north and south. So it's that way. And somebody's got a compass underneath there. Okay, it says, assume the compass is at a location on Earth where the compass would ordinarily point due north. All right, don't know if you knew this or not, but compass needles do not point toward the north geographic pole. They point toward the north magnetic pole. And there's, I don't know how many 1,000 kilometers between those two, but they're a ways away from each other anyway. I think when I lived in Minnesota, seems like the magnetic declination there was close to 0. So it's on a line where there's farthest north is the north geographic pole. As you go due south toward Minnesota, you would pass over the north magnetic pole, and then you'd get to Minnesota. But in Washington, it seems to me it's around 19 degrees or something like that. You take whatever direction your compass needle is pointing, and you can set this on a good compass. 19 degrees to the west of that would be true north. So that's something that happens. But this happens to be at a location on Earth where the compass would ordinarily point due north. So B for the Earth is pointing due north with this magnetic field strength, 0.55 times 10 to the minus fourth Tesla. And we're going to be adding to this magnetic field the magnetic field of a wire, and we want the compass needle to point 30 degrees east of north. Well, the compass needle is going to be responding to this magnetic field and the magnetic field of the wire, and so we'll have a B for the wire that has to point to the east. I'll make B for the Earth a little bit bigger so that the sum of those two makes an angle of 30 degrees. And we just have one significant figure on that. So we're just over after kind of an approximation here. Well, what we can see from this is that B for the wire over B for the Earth, that's going to be the opposite side over the adjacent side, is going to be equal the tangent of 30 degrees, or B for the wire is going to be B for the Earth, tangent of 30 degrees. But B for the wire is going to be 0.65 meters above the compass. Now, what direction will the current flow have to go to make the magnetic field point to the east when you're underneath that wire? East is this way, by the way, and west is this way. Any ideas? You just got your first shot at it today, actually. When you've got current in a wire, if you point the thumb of your right hand in the direction of the current, your fingers will curl in the direction of the magnetic field produced by it. So if the wire current was going north, then on top of the wire, it would point, the magnetic field would point to the east, but underneath the wire, it would point to the west. So the current's going to have to be going in the opposite direction. That way, the current's going that way. Underneath the wire, which is where this compass is, then the magnetic field of the wire will point to the east. And so that's something that we know. So this has to be the direction of the current flow, I in that direction. And the magnetic field is going to have this for a magnitude. And I'll probably hang on to two significant figures. I'm planning to rewrite this problem with more sig figs on that. Makes it halfway interesting. And we're given everything else to two significant figures. So magnetic field of the Earth, 0.55 times 10 to the minus fourth. And that 10 to the minus fourth Tesla is a Gauss. I think I mentioned that. We're not going to use those units, but they do show up once in a while. And for the magnetic field of the wire, it will equal 3.2 times 10 to the minus fifth Tesla, but it will also equal mu naught I over 2 pi r, where r is that 0.65 meters. And so the current is going to have to be, we can solve that here. Current will equal 2 times pi times r, which is 0.65 meters. We'll see if we come up with amperes on here. Times B, the 3.2 times 10 to the minus 5th Tesla. And then on the bottom, I'll have mu naught, which is 4 pi times 10 to the minus 7th units, which I can never remember. I've got too many units floating around in my head. Where did I put it? There it is. Okay. Tesla meters per amp. Hey, it works. Okay, Tesla meters on top, Tesla meters on the bottom, 1 over amps left on the bottom, and I'll end up with amps. So let's see, and 2 pi over 4 pi just gives me a 2 on the bottom. That times 0.65 meters. I think I get about 1.0 times 10 squared amperes if I didn't foul up punching that stuff into the calculator. So about 100 amps for a current, which isn't unheard of. Well, actually, power lines can have a lot more than that. This isn't very far above the compass. I don't know if I'd want a wire carrying 100 amps where it could only be, that fraction of a meter above your head. That could be a little dangerous. So, okay, any questions on that one? These are fairly complicated problems we're diving into here. The next one's a similar problem. You might take a look at that one overnight. Excuse me. And just see what you can do with it. And don't really have time to dive into there. It uses the same strength for the Earth's magnetic field. So at least this one's a ways above the ground, 5.5 meters. But still not all that high to be carrying 800 amps. Okay, well, I think I'll stop there. For the lab this week, I think I'm going to finally post the I can't remember what I named the lab, but it'll be one involving your little electronics kits and taking some various measurements on there instead of just dealing with resistors in series and parallel. You'll actually have some power connected to it this week. So, although it may just be from a 9-volt battery too. But we'll get that posted here before too long. All righty, I'll turn you loose. And that's our introduction to the Biot-Savart law, and we'll be spending a few days on it. And then we'll move on to something else with magnetism that's a connection between electricity and magnetism. We do kind of have a connection here that the moving charges make a magnetic field. So we'll take off from there.